So I want to talk about a few more functions. Next up is a function that we spent some time on already, but I want to think about f of z as e to the z and what that looks like when we graph it. And so let's look at a picture here. So I'm going to look at, I'm going to look at f of z is e to the z. So that's going to look, that's going to be like this. Nope, wrong picture. Okay, it's going to look like this. So this is f of z is e to the z. And this is what the picture is going to look like. And so again, all of these functions that we've talked about so far are conformal maps. I want to make this a little bigger. So all of the functions that we've talked about so far are conformal maps, meaning that they're angle preserving. So if the inputs meet at right angles and the outputs meet at right angles and so on. And you can tell that each of these grid lines, of course, over here, these are very clearly right angles. Over here, these are also all meeting at right angles, right? If we were to look at any of these angles here, that would be a right angle. Okay, and so on. So this is f of z is e to the z. And again, a little bit subtle here, what we need to do with f of z is e to the z is we have to, if we're talking about this function, f of z is e to the z, we need to specify that z is x plus I y, and then y we need to give a range. So this is the branch cut issue that we dealt with the square root. But we need to talk about what are the values of y that we're allowing. And again, this has to do with figuring out what's the inverse and how's the inverse going to work. So we can let y be anything that we want. Let's say y is again between negative pi and pi. Okay, and so this is what we're going to allow for the function f of z is e to the z. And if we want to, in this case, if we want to allow one of them, that's fine. Typically we don't. Okay, so typically we do not. So this is what the function f of z equals e to the z looks like. We've already talked about some properties. So it has all the usual properties of e to the z times e to the w is e to the z plus w, e to the 0 is 1. The modulus of e to the z, this is not something that we've talked about, but this is important. So the modulus of e to the z is the modulus of e to the x plus iy, which is just the modulus of e to the x times the modulus of e to the y. And of course, the modulus of e to the x is itself, because e to the x, if x is real, then e to the x is positive, so we can just drop the absolute value. E to the iy is modulus 1. And so this is our modulus r. Okay, so this is a useful fact here. That's why we're allowed to call e to the x our r, and then y as our theta. And that's kind of the angle that makes there. Okay, and so this is e to the z. Not too much more to talk about that. E to the z, I do want to mention a few things here. So if we were to have e to the z equals 1, it turns out that the only solutions here is when z is an integer multiple of 2 pi I. So z is 2 pi I k for some integer k. Okay, so for some integer k, integers being -3, -2, -1, 0, 1, 2, 3, and then infinitely far in both directions. Okay, so positive and negative whole numbers and 0. So e to the z is 1 if and only if z is if z is 2 pi I k. And the reason why this is useful is that it's important to talk about some properties of e to the z. So this function f mapping the complex numbers to the complex numbers given by f of z is e to the z is what's called a one-to-one function. So this function is what's called one-to-one. And one-to-one means that the only two values, so one-to-one means that if you plug in different inputs, you get different outputs. That's one way to say it. Or to say it a little bit more algebraically, if f of z equals f of w, the only way that can happen is if z equals w. Okay, so this is saying the same thing. If z is not equal to w, if you have two different inputs, then f of z and f of w are not equal. Then you have two different outputs. So different inputs give you different outputs. That's what a one-to-one function is. Notice that f of z equals z squared is not one-to-one. So f of z equals z squared z squared is not 1-to-1. Since, just for example, f of I and f of minus I were both -1. So those were the same output, but I and minus I are clearly different inputs. So that was a function that's not 1-to-1. But it turns out e to the z is a 1-to-1 function. Okay, so f, let me just write it one more time. F given by f of z equals e to the z is 1-to-1. And the reason why we know this is that it's a 1-to-1 function because if you were to take f of z equals f of w and set them equal, that would imply that e to the z is equal to e to the w. And that would imply that e to the z minus w is 1, if you just divide both sides by e to the w. And we know that this means that z minus w is some integer multiple of 2 pi. Okay, so that's what we just said in the step above, or just in the step right before that. And this is for some integer k. Okay, for some integer k. And the reason why, what this actually means is that z minus w is equal to 0, because the only values that we're allowing are from negative pi to pi. So if we want to talk about what are the values from negative pi to pi, where we have integer multiples of 2 pi, well, the only one is 0. Okay, so that means that this only happens at that angle 0, and therefore z is equal to y. Z is equal to w, excuse me. Okay, and so this tells you that the function is 1-to-1, meaning that any two different inputs go to two different outputs. The reason why that's important is that it turns out that 1-to-1 functions, you need a function to be 1-to-1 in order for there to be an inverse for the function. So there is no nice inverse of f of z equals z squared unless you have to make some sort of definition or restriction or branch cut, which if you notice when we talked about the square root of z, we had to do that. And the reason is that f of z equals z squared is not 1-to-1. So that means that there's no reasonable way to define the inverse function if we don't make some choices. And so we talked about the choices that we had to make in order for the square root of z to be defined. Likewise, we have to make some choices for the exponential function in order for the inverse to be defined. And so what we're going to do is we're going to define the following. So let's think about the function f mapping the complex numbers to the complex numbers given by f of z equals e to the z, where we're going to take the argument of z, that theta angle, to be between pi and minus pi. And again, there's nothing special about the interval from minus pi to pi. You could do, from pi to 3 pi, or whatever branch cut you want to do is totally fine. This is just a choice of convenience, really. And so what we're going to do is we're going to define a function which is going to be log of z. And it turns out that this will be the function that will be the inverse of our exponential function. Okay, so log of z. And so a little bit of what we need to do here. The right way to define the log of a complex number, turns out what we're going to do is we're going to take the natural log of the absolute value of z. Okay, so the natural log of the absolute value of z, sometimes people just write log for the natural log. Mathematicians like to think of logs and natural logs as the same. The natural log is the only log that matters to mathematicians, more or less. If you do computer science, then the only log that matters is log base 2, but if you do math, the only log that matters is the natural log. Anyway, so this is plus I times the argument of z. And again, the argument of z is going to be that value between negative pi and pi. So for example, if I wanted to talk about the log of whatever, I plus 1, log of 1 plus I, this would be the natural log of the modulus of 1 plus I, which we'll talk about what the modulus of that is in a second, plus I times the argument of z. And so what we have to do is we have to think about 1 plus I is this number here, And it turns out that you can do this kind of in general if you want, but there's this is a nice point. It's not an arbitrary point. It's one that's picked out so that this is nice. And so the argument between negative pi and pi is going to be pi over 4. So pi over 4. And so the modulus of 1 plus I, if you were to think about what's the modulus here, that would be square root of 2. So this is the natural log of the square root of 2 plus I times pi over 4. And that's going to be how it turns out we define our log term. Now, this is completely dependent on our branch cut for the exponential function. If the exponential function, so I just want to point this out, if our exponential function was defined so that we had, say our argument was, say, 3 pi to 5 pi, just to do something silly. So if we were to have 3 pi plus to 5 pi as our argument, then what this would mean would be that now it turns out what we're doing is we're excluding this value. I'm sorry, we're excluding, we're still excluding this value. We will go from 1 to, so we would go from 3 pi to 5 pi. That's how that would work. And then the value here that's going to be relevant for us is going to be 4 pi plus pi over 4. So it turns out that if we were to think about the log of 1 plus I, where we determine this to be the this to be our branch cut, we would still have the natural log of the absolute value, 1 plus I arg 1 plus I. And so that would still be the natural log of the absolute, the natural log of the square root of 2. But here the argument would be 4 pi plus pi over 4, which would be 17 pi over 4 times I. Okay, and so that's how the choice of our argument is going to affect our function. Okay, and so that's why we always have to determine what this branch cut is going to be ahead of time. Now, once we have a branch cut, and you can do this in general if you want, you can think about if you want the argument to go from, say, some point to that point plus 2 pi, you can do this in general. I'm just going to do this from negative pi to pi. But what this means now is that now we have an inverse of the exponential function, so that e to the log of z, so e to the log of z is going to be e to the natural log of the modulus of z plus I arg z. And so this will be e to the natural log of the modulus of z, which we'll talk about in a second, times e to the I arg z. And this is e to the natural log of r, if z is r e to the I theta, and e to the I theta, right? So this is r e to the I theta, or just z, if we're calling z r e to the I theta. Okay, and so this is how the two terms undo each other in that sense. Okay, so e to the log of z is just going to be z. And again, the thing that we had to really pay attention to, which I just completely glossed over, but which I need to go back and pay more attention to, is determining this value I arg z is dependent on the branch cut that we use for the exponential. So if we use the branch from 3 pi to 5 pi, this I arg z is going to be a slightly different value than if we had something else. So again, we have to be really careful here. So e to the log z is just going to be z. So in this sense, they're going to be inverse functions that undo each other. So at this point, let's talk about the graph. Let's look at f mapping. It's not quite mapping the complex numbers to the complex numbers because not all complex numbers can be plugged in. But what we're going to do is we're going to look at the function f of z is log z. And so I just want to remind you that the exponential function, sorry to scroll here, but the exponential function looked like this. It took kind of these squares or rectangles into circles. And so you can imagine that the logarithm is going to do the opposite. Okay, and indeed it does. So if we were to look at the logarithm, let's see, we would have, there we go. So there's our log function, f of z is log z. So it takes, again, you're missing this little negative part of the imaginary, the negative part of the real axis, and then it's going to map that back to the real value z. Okay, so that's the log function.